the participants to come inside. We are going to start the session, please. And also, hotel management, we want a little bit of less light in the front. Technical session, morning session, is the geomorphology, stratigraphy and paleontology and tectonics. This is Hall A, and I'm Vishal Reddy. I will chair the session, and my co-chair is Professor Dr. Mary Hutler, and our professor is Krishna Kumar Shrestha. The first speaker is Mike Searle, Professor Mike Searle. There is half an hour time is given. It's a keynote speech by him. As you know, he is just today honored as an honorary member of the Nepal Geological Society, and his title is Mount Everest: Tectonic Evolution, Uplift, Exhumation, River Capture, and Models. I invite Professor Searle to begin this talk. Thank you.
Thank you very much, Michelle. As everybody knows, the highest mountain in the world, and it is one of Nepal's great, fantastic features in this wonderful country here. I've done about 7 years field mapping and geological work on both the Nepal side and 3 years on the Rongbuk side in Tibet. To put the place in context, I'm sure everyone is aware of the geological features here. In the black line is the main collision zone between the Indian plate and Asia, the Indus Suture Zone, which runs for 2,500 kilometers along the north side of the Himalayas in Ladakh and South Tibet. Everything south of the black line is the major Himalaya, with the Tethyan Zone in this. Where do I point? The Tethyan Zone is all the northernmost part of the Himalaya, and the Greater Himalayan sequence is bounded by these two green lines, which are the South Tibetan Detachment normal fault in the north and the main central thrust in the south. The active boundary of the Himalayas is the black line in the south, the main boundary thrust. Everest spans the northern part of the Greater Himalayan sequence and just the southern part of the Tethyan sequence. So how do we know when India and Asia collided? There are various ways of defining it, but the one that I feel is the most robust age is the final part of the marine sedimentation of the Tethyan Suture Zone, which this photograph in the bottom is taken from a Mount Indian Tingri in South Tibet, and it shows beautifully the transition from the marine sediments, the white, which are shallow marine limestones of Eocene age, up to the continental molasse deposits. By this time, 50 million years ago, there was no more ocean between India and Asia. And that's when the crustal thickening started along the Himalayas. Some of the oldest kyanite ages we have, uranium-lead monazite ages, are as old as 45 million years. And following that, there was continuous crustal thickening right the way up to the present time. So here is a Google Earth image showing the Everest region. It's a little bit busy, but Everest is right in the middle. The South Tibet Detachment is the fault in red, that is very shallow, dipping to the north, and it offsets both the Everest part, which is the Greater Himalayan sequence, and the Amadrima part, which is the deep crustal equivalent rocks underneath Everest. So the result of this 7-8 years mapping in Nepal and Tibet is the geological map of the Mount Everest and Maklu regions that I have made. The latest edition is 2007, and I have a few copies of it here for anyone who would like. The map centers on Everest right in the middle, and the black lines are showing the transects, where I'm going to show you the cross-section, north-south cross-section, and then the east-west lateral section. The leucogranites, which make up the base of Everest, are all in red, and the South Tibetan Detachment follows the contours all the way down the Rongbuk Glacier until it dives off underneath the Tibetan Plateau, and the brown rocks on the map in the north are all these sedimentary rocks, the unmetamorphosed sedimentary rocks at the base of the Tethyan sequence. So here is a north-south cross-section going through Everest, and you can see that the uppermost summit area of Everest is cut by the Chomolungma detachment, which is one of the branches of the South Tibetan detachment. This is an absolutely unique structure anywhere in the world. It's a low-angle normal fault, about 10 degrees dip on the summit of Everest, flattening out almost horizontal underneath the Changtse region. And then obviously go along the Rongbuk Glacier in Tibet, it dives gently off to the north, and it puts unmetamorphosed sedimentary rocks of Ordovician age above high-grade metamorphic rocks of the Greater Himalayan sequence. There's about 400 degrees and about a 3 kilobar jump in pressure across that fault. Here is the lateral section showing that the leucogranites are these incredible structures that, again, you don't see pretty much anywhere else in the world. They are very thin sill complexes of leucogranite intruding sillimanite gneiss. Some of the biggest sills are about 1 kilometre or even 2 kilometres thick. And they go on for 100 kilometres. You can trace the same leucogranite from Everest Base Camp on the Nepal side all the way down the Rongbuk Glacier for 70 kilometres. And these sills have come a very long way. And these are almost unique structures in the world when it comes to S-type granite replacement mechanisms. When you reconstruct the Greater Himalayan sequence, this is a very rough sketch of what it looks like. The main central thrust in the south, which is mapped as the base, the brittle fault that remains at the base of the inverted metamorphic sequence, going right the way up to the South Tibet detachment on Everest and the Chomolungma detachment at the top. And you can see that most of the Greater Himalayan sequence is Neo-Proterozoic. All the sillimanite gneisses you see from Lukla all the way up to Namche Bazaar are metamorphosed Proterozoic orthogneiss, overlaid by the Cambrian unit, which is Unit 2. These are the big algal structures that you see all along the Himalayas of about 500 million years. And the Ordovician, which is the summit rocks of Everest. So this is one of my PhD students, Michael Jessup, did a very intense series of pressure, temperature, thermobarometry results all the way along the Dudakosi River from Caracola through Lukla all the way up to the Everest series in Everest. It's far too detailed to go into here, but basically there is the thickest section of sillimanite gneiss anywhere in the Himalayas in the Everest profile. So when you go off the plane and look like, you're already in sillimanite grade gneiss, and it goes all the way up through the lignite zone up to the leucographs. This is again the section running through the top. When you get to the upper part of the Greater Himalayan sequence, the South Tibetan detachment here is beautifully exposed in a little valley, the Zaka tube, which goes into one of the rivers that is captured by the Arum River to the north of Everest, and it's an incredibly wide shear zone of high-grade metamorphic rocks and leucogranites at the base, passing quite gradually all the way up through breccious fasces to unmetamorphosed sediments at the top. And this structure is the same all the way along the Himalayas. The beauty of the Himalayas is that it's actually a very simple mountain belt. You can follow a north-south profile pretty much anywhere from Zanskar to Karwal to Western Nepal to Everest to Arunachal Pradesh, and you go through a very similar set of structures in inverted metamorphic rock. So this is the section through the Dhaulagiri profile, the Kathmandu, where you see the South Tibet detachment is sprung into about 3 different displays of the normal fault. Dhaulagiri and Annapurna are 2 of the only 8,000 meter peaks which are exposing the base of the Tethyan sequence. So they are mostly Cambrian, thick Cambrian dolomites and limestones going up into the Ordovician. And the Greater Himalayan metamorphic sequence here is condensed. It's much, much narrower than it is on the Everest profile. So one of the best sections showing displays of the normal fault on Everest is on a mountain called Kang, which is to the west of Everest. It's between Sherwood and Everest. And the west face, this beautiful picture was taken by Marco Results, a climbing friend of mine. And it shows the upper Chemolanga detachment putting unmetamorphosed sedimentary rocks above Everest series storite andalusite grade gneisses with another brittle detachment, and then you're into the granites. From here, all the way down to Caracola is in siliconite grade, partially naked. On this picture here is looking at the north face of Everest from the Tibet side, the Rongwood side. And the big detachment is this one here, the Chemolanga detachment. This puts upper Cambrian and lower Ordovician rocks at the summit ridge of Everest over the yellow band, famous yellow band, which is composed of Cambrian calcosilicates, probably deposited about 510 million years ago, but they're now metamorphosed into calcosilicates at 3 or 4 kilobars, 400 degrees centigrade. And then you go down into the Everest series, where the metamorphic isographs are right way up, with a sudden break at the top along the Chemolanga detachment. This is the main climbing route up Everest through the western Coombe. So Everest Base Camp on the Nepal side is just down on the picture to the lower left. And it shows the Everest lithogranites, which are, they're not cut by the faults as you see in Kang, but there's a fault right above it, which determines, puts Everest series rocks over the lithogranites and the gneisses. South Col, 7,900 metres, is off to the right, and the main climbing route is up from the South Col to the summit. Whoops, this is getting crazy. Boom, exactly. Okay, so the stratigraphy of the upper part of Everest is actually quite well known, and it's very comparable to the stratigraphy we see at the Cambrian Ordovician, both in the Zanskar Valley, Spiti, Bahul, all the way along the Himalayas. Now that has gotten a little bit crazy, but these are thin sections. The photograph on the left was actually collected by Ed Hillary on Summit Day, 1953, 29th of May. That rock is clearly a sedimentary rock. It's a limey mudstone, and it's full of little artifacts and fossils. Crinoids, trilobite fragments, all sorts of things in there. The rock on the left, on the right, is the yellow band. It was collected by Charles Evans a few days before the first attempt. And this is clearly a metamorphic rock. This is one of the marbles metamorphosed at about 400 degrees centigrade. So we have about 25 samples from the summit rocks of Everest back in Oxford. And crinoids are sea lilies that you see in the present day oceans, and this is a cross-section through the stem of a crinoid with a little fragment of trilobite at the bottom. Sorry, this is really not working properly. Okay, so beneath the summit, you have the Chemolanga detachment, the yellow band, and then you're into the Everest series. And below the Everest series is this incredible network of lithogranites. These are garnet, muscovite, tourmaline-bearing lithogranites, which are 100% crustal melts. They have hugely high strontium initial ratios. They're produced by partial melting of a black shale, probably the Neoproterozoic, what we call the Hymantic complex in the west. And you can see the bottom part of Lintren. Lintren is just next door to Everest Base Camp on the west side. The upper part is a huge sill. It's over 1 kilometre thick. It contains sealers of the siliconite gneiss. The bottom part is a layered sill complex of true siliconite gneiss. Again, just around the corner from Everest Base Camp, on the way up, you see this beautiful view of the west face of Nuptse, which is part of the Everest-Lhotse-Nuptse Ridge. And this lithogranite we dated at 18 million years on uranium-lead zircon. It has all the phases to it, and it's underlain by ductile shears and Nuptse ductile thrust. Right across the valley, there's this fantastic mountain, Amadabla. Everybody climbs it from the south, but if you go around to the north side, there is this spectacular outcrop of one of these Everest granite sills coming at the bottom, dated at 21 million years, and it shows little veins, dikes, intruding magma up to the uppermost sill complex, which underlies the rocks of detachment and extends all the way down the Rongbuk Valley through Changsi. This picture here is taken by a friend of mine from the summit of Everest, looking straight north down the Rongbuk Glacier. And you can see the Lhotse detachment, the Chomolungma detachment goes for at least 75, 80 kilometers from Everest to the north. And you can map this in intricate detail. So my map extends down to the northernmost part of the Chomolungma detachment as it disappears under Tibet. You can see the detachment also encircles the peak of the Changsi. This picture again is from the summit of Everest looking west to the mountains of Chaoyi, Kang. Chomolungma detachment clips the top of both of those mountains. I showed you a picture of Kang from one side with the two detachment faults in. And all of the country to the south, Lingtren, Mori, all the way down south of Chaoyi, is all in leucogranite, sillimanite gneisses and nucleotides. Probably the most incredible part of the leucogranite story in Everest is on the Kangshan Glacier, which is the east side of Everest, coming in from Tibet. This is in the core of the Himalayan melt zone. And you see these amazing rafters. There's rafters the size of this room, some the size of this hotel, surrounded by the main Everest leucogranite. We've dated the various parts of the metamorphic story, which go back to 39 million years to 20, and the main leucogranite ages 20 to 60. And the youngest leucogranite ages, this has got a mind of its own. The youngest leucogranite ages are exposed in the northern part of the Rongbuk Valley. So here is my colleague Rick Lord, who I've done a lot of this work with. Rick's a structural geologist. He looks at the strain and fabrics all the way along there. And a lot of this work was done with our two students, Michael Jessup, who looked at the pressure temperature thermobarometry, and John Cottle, who did a lot of the uranium lead dating of the granites, both zircons and monazites. And these profiles here are taken from Hermit's Gorge, which is very close to the advanced base camp going up the Rongbuk Glacier, and you can see the early leucogranite sills within the sillimanite gneiss are cut by this later set of three. So the youngest granites we see at the Rongbuk are about 15.4 million years. Here's another close-up of that same outcrop. This outcrop we pulled apart by dating every phase of leucogranite coming out. And all of these leucogranites are truncated at the top by the brittle fault, which cuts everything but sediments above these rocks. This is another outcrop here showing the Sec 1 sills, some of which are isoclinally folded within the sillimanite gneiss, cut by the Sec 2 dikes, which are relatively undeformed, and the whole lot is cut by the Sec 3 dikes at 15.5. This thing needs advancing. This is at what's called now the advanced base camp at Everest. So this is up at what used to be the old Camp 3 in the old British expeditions. The North Col is just above at 7,000 metres, and this is the peak of Changsi to the right. And again, it shows the Everest series sitting on top of these leucogranites with a ductile shear zone in lots of detachment underneath. This is taken from the lower parts of Changsi Peak, looking across the upper Rongbuk Glacier. Everest is just off to the right. And one of the most incredible parts, we've also spent 3 years mapping around the Makalu region to the west. And the Makalu area is again fairly unique because the entire upper part of Makalu is composed of a cordierite-bearing granite that you don't really see very much of in the Solukhumbu or in Rongbuk. And you can see here one of the feeder dikes for the cordierite leucogranite feeding the whole summit sill. It's cut cutting all the earlier Everest-type granites, which are the Garnet 2 microlate granites. So just to give you some idea of the complexities of the granite intrusion, this is a boulder, a single boulder, somewhere on the upper Barron Glacier on the south side of Makalu, which shows 6 phases of leucogranites, each one cutting the other one. We've dated 4 of those phases, and the youngest one is up at about 12 million years. So the further north you go, the younger the lunar granite. But they are incredibly complicated rocks. So to put this all into a model, this is the model of channel flow, which was actually contrived back in the late 80s by structural mapping, combined with strain work, the sort of work that Laura and Michael Jessup do, looking at quartz fabrics all the way through. And both the main central thrust and the south Tibetan detachment are faults. You can only define them on strain and structural criteria. You cannot use stratigraphy, you cannot use detrital zircons or isotope work to define the faults, because faults cut up and down stratigraphy. So when you look at the metamorphic story of the Greater Himalayas, you see below the shear zone at the top, the South Tibetan detachment, you have a right-way up series of metamorphic isochords, which are all condensed into a huge ductile shear zone. And this is apparent for at least 2,000 kilometers along the length of the Himalayas, at least from Zanskar to Bhutan. On the south side, you have the main central thrust. There's been a lot of arguments about the main central thrust. Again, you can only define a thrust fault on strain criteria. You cannot define it in stratigraphy or detrital zircons or anything else. They give you information about stratigraphy, not structure. And as we've seen, you have the same rocks in the footwall and the hanging wall, the neoproterozoic gneisses along the main central thrust. So the MCT is defined as the base of the inverted metamorphic sequence going from selimonite, migmatites up at the top, down very rapidly through kyanite, staurolite, garnet, biotite, huge strain zone at the bottom. And it's the ages of the leucogranites that define the timing of channel flow. So channel flow was operative along the high Himalayas from at least 24 million years to 16, with the youngest leucogranites coming in at 12. After that, melts ran out, the whole system locked up, and structures propagated down to the lesser Himalayas and eventually the main boundary thrust of the world.
5 minutes more, please.
Okay. So to explain the low angle normal faults of the South Tibet detachment, this is again an incredibly interesting, really unique structure. It is a huge low angle normal fault which varies from 50 degrees dip or so in some parts in the west to almost horizontal to 5-10 degrees as you see along the Rongbuk glaciers. And what you have to do is to combine, you have to extrude, you have to flow these leucogranites, which are forming at 4 or 5 kilobars down, say 20-25 kilometers, and you have to juxtapose them next to unmetamorphosed sediments and the Everest series at the top. This is exactly the same structure on Dhaulagiri. To the west, you have 3 rock types here. The clinopyroxene tremolite marbles. These are high-grade marbles formed at 9 kilobars, getting on for 40 kilometers depth. And then there, the green box there are the kyanite gneisses. You have to bring those 2 deeply buried rocks up to juxtapose next to unmetamorphosed sediments at the base of Dhaulagiri. And the only way you can do that is by channel flowing it up the rocks. And that was the crux of why these normal faults are there. These are low angle normal faults in a wholly compressional environment and nothing to do with extension. Okay, if you look at the fabrics as well, the fabrics are incredibly interesting because all of the fabrics as you climb up towards the Great Himalayas are thrust relays at the top to the south. When you cross the selimonite feldspar melt isograph, the first leucogranites start coming in, everything is top to the north. That does not mean crustal extension, it means extrusion of footwall rocks along the base of the South Tibetan detachment. This is a summary paper of all the geochronology we've done on Everest, both on the Nepal side and the Rongbuk Glacier, which was published a few years ago, along with quite a bit of other stories. We don't have time to go into any of the low temperature thermochronology, but the interesting thing is it's all relatively old, but immediately following the cooling of the granite, so the granites cool very, very quickly, then the whole thing locks up by 8 million years. It's just been passively uplifted by underthrusting along the lesser Himalayas to the south. So So this time chart on the right concludes all the main chronology of evidence from crustal thickening, kyanite grade metamorphism, decompression from kyanite to sillimanite grade from about 12 kilobars to about 8 kilobars, sillimanite muscovite melting, producing the Himalayan granites and the timing of channel flow. All of that cooled very, very quickly, 17, 16 million years. Brittle faulting on the South Tibet detachment, brittle faulting at the base of the NCC, probably around 15 million years. And we have a very steady state cooling as it's passively uplifted by jacking up from underneath until you have the onset of glaciation about 2 million years ago. And then you see geomorphology like we see today. So these are all the people I would like to thank, particularly the fieldwork team, Rick Law, Michael Jessup, John Cothell, Mike Straw worked in the Macaulay region, and of course Mary Hubbard, the great queen of the Kathmandu Himalayas, did a lot of early work on the main central thrust, way back in the Precambrian.
Thank you.
Okay, I won't go into any of this because I'm sure Laurent will talk about the GPS and the active history. There is one thing I would like to say is a paper came out in Nature very recently relating the uplift of the Chumulunga Everest to river drainage piracy. I don't like this paper at all, and there's 100 reasons why. A lot of it is to do with there are absolutely no age constraints at all. The capture of the Arun River by the Sunkosi, that's 50 kilometres to the south. It's a trunk river, there's no river capture there at all. The rivers north of Everest, in Sakatune, that's river capture, but this one is not. The Arun is probably no different from any other river, it's just in size much further to the north. So the only truly antecedent rivers in the Himalayas are Yarmung Zangpo, Brahmaputra, Sutlej, Kaligandaki, and the Indus. The rest are just enhanced river erosion as you go. And I've obviously run out of time, so I will stop there. But just to say, I do have a book, Colliding Continents, which is available in all good bookshops in Tamil. And I have one copy here for anyone who would like to see the whole story of the last 30 years' work on the Himalayas. Thank you very much. Thank you much.
Thank you, Mike. We may have one or two questions, time for maybe one or two questions. If you have any questions, please. Okay, here. I'm a friend from India, Sagar University.
I have some queries. What do you think, how the pegmatite is formed? Is the pegmatite is formed by the breakdown of muscovite or something else?
It's mostly muscovite melting. It's the end product of regional metamorphism.
Yeah.
So as you go up whole sequence, you go garnet, chlorite, kyanite, sillimanite.
Or muscovite and quartz give rise
Sillimanite
to
plus muscovite.
sillimanite orthophase and
Sillimanite, muscovite, feldspar. As soon as that comes in, you're into the melting zone. That's where the big.
And another query is there. You have mentioned garnet, biotite, tourmaline, lithogranite.
Yeah.
How the garnet is formed in lithogranite?
Garnets are well known to form in S-type granites. Granites produced by crustal melting of continental rock. They never occur in I-type granites.
Yeah, I know that.
Mineralization.
Yeah.
Well, garnets is a mixture of iron, manganese, magnesium, calcium. You have all those elements in the granite. So
Why don't it can be called as a leptinite?
for what?
Leptinite?
I've never heard of that.
Okay, I think we're going to discuss more later on. But if you have any other questions from the audience, please.
Thank you, Professor. Sir, you are very nice and great talks. I am Kaviraj Paudel from Central Department of Geology. And here my concern basically two. One, if we see the Himalaya, and because you have done a lot of work on tectonics, metamorphism and deformation, and we see the windows in the east and naps and cleavage in the western part. So what type of tectonic prevails this structure? Mostly the large windows in the eastern part and the naps and cleavage in the western part of the Himalaya. One my query. And second, you have talked about normal faults. So what field evidences are over there? Did you find the shear sense indicators to support these normal faults, or how do you say these both are the normal faults based on the field evidences? Thank you.
There's shear sense indicators everywhere in the Himalayas. They're beautiful rocks for determining strain and sense of shear directions. Sorry, what was your first question?
Yes, about the naps and
Oh, the naps.
windows.
Okay, well, the whole Lesser Himalayas is just a standard fallen fold and thrust belt. These are very common in all mountain ranges, and they generally start with fallen and propagating thrusting. So the thrusting starts off in the Indus Suture zone through the Tethyan series, the Greater Himalayan during the late Eocene up to Miocene, and then when all the channel flow stops and the metamorphism ends in the Greater Himalayan, structures propagate down to the Lesser Himalayan. So in Langtang, for example, the metamorphism decreases in age as you go south, and then the whole of the Lesser Himalaya are folded. So you have the Kathmandu syncline, which is underlaid by thrust, and all of the windows are formed by late-stage folding of the Lesser Himalayan naps. The early structures are all beautiful fold naps, and the later structures are gentle folds that you see like around Kathmandu.
Thank you. I'm T.P. Adhikari from Trivandrum University. I thank you very much for your comprehensive presentation. So, my query is, looking at geology, physiography, topography, the eastern part of Nepal has higher elevation. For example, most of the higher peaks are located from Dhaulagiri eastward, and there are some eclosites in the Arun Valley. Therefore, how do you explain the elevation in the eastern Nepal and western Nepal, and what are the reasons behind that?
I don't think there is a huge difference east and west at all. The difference is all in geomorphology, glacial erosion, very young metamorphism. But there is no real difference in ages or strain anywhere along the Himalayas. I can show you identical sections of this in Zanskar and Peru. And so the reason that you've got big mountains in Everest show you, they're just a little bit higher than the rest. It's no big deal. And this is the point of that nature paper. They had a completely unconstrained uplift of 15 to 50 meters of Everest by a river capture that happened 50 kilometers to the south. This cannot be correct.
Thank you. So, thank you so much, Mike, for your excellent talk. Now we go to the next our keynote speech talk by Dr. Vedra, Professor Vedra Misal. The topic is stratigraphy of Nepal, this is Himalaya, a critical review. You have in Nepal, you have 5 minutes for presentation and 5 minutes for question answer. Please continue. So 25 minutes for your presentation, 5 minutes for...
Thank you. Today I am talking about very simple but complicated story of Lesser Himalaya, where we are facing with very many stratigraphic issues. These issues are critical because depending upon the model the researchers use, or depending upon the rigor of the study, we are having a large number of formation names, and some of them are duplicates. They are same rock types, same stratigraphic positions are named as different types. On the other hand, different rocks are put under the same stratigraphic column. So this kind of situation is very embarrassing, and I would like to just highlight upon this issue in some of this present talk. I will give the history of stratigraphic investigation, then stratigraphy and lithology. And another important point is the stromatolites. Whenever we see stromatolites, it happens that they are all belonging to the same unit. That is probably not true, and I will explain that point. And the question of correlation is very critical and it is very complicated. Next one, please. Let's go back to Hagen. Today we had the medal, Tony Hagen medal, and we see here actually all these. I think the pointer is not working. Is it? I cannot just. I just show you the windows. I think everybody knows this, and we can do here windows and large sedimentary belts here, and the cliff over here. So Hagen was not interested in unifying different rock units. Therefore, in his 3 sheets geological maps, divided into 3 parts, he has given a large number of units in each sheet, and he was not interested in making a unified classification of these lesser Himalayan rocks, as you can see here. Similarly, Hagen Dancer, while working in West Nepal, they first time prepared columnar sections and showed the position of like stromatolitic dolomite. And in Kuma, they worked out their stratigraphy and continued towards Nepal. Bode and his colleagues were the first person to work in East Nepal, and they prepared a good geological map with quite reasonable stratigraphy given there. When it comes to Fuchs and Frank, they are of the opinion that there should be one unified stratigraphy throughout Himalaya. And others like Hashimoto, Talarov, and C.K. Sharma, they didn't work on the stratigraphy of this area. Though Hagen had this variety of rock names, sometimes he borrowed some names from the Alps like Vericano and others. So these were some exotic names he borrowed from the Alps. Next, please. Here, this is the map prepared by Fuchs, and you can see the lesser Himalayan rocks here, and within the windows here, and especially in Nepal here. So he is of the opinion that there should be unified stratigraphy, and they're basically divided into metamorphic, low-grade metamorphic rocks, and the sedimentaries containing carbonates and slates, basically. So these units, he first worked out in India, in the Cloud Belt, in Simla area, and then following Metricot and Odin, he tried to extend them throughout the Himalaya. Next, please. So here we have a map where we can see basically these are phyllites, quartzites, carbonates, and slates. Basically what we see, except for some tertiary beds in between. Most of them are gneisses, phyllites, quartzites, and slates, and dolomites. So here, in fact, it is a lithological map, rather a lithological map than lithostratigraphic map. So the problem arises because we are working in a Proterozoic sequence where the age is about 1.5 gigayears. So it's a very long span of time, and it is very improbable that during such a long span of time we have only one dolomite band, only one quartzite band, or only one slate band. So that was the problem. And this problem was first worked out by Stocking in this part and Sakai in this part. These two geologists were first persons to work out the stratigraphy and decent stratigraphy, excellent stratigraphy from here and here. They didn't just make columns or maps, they covered very large area and defined their units in this part as well as from this part. Next one, please. The problem is, as we don't have fossils, so we have to if you move from north to south or from south to north in this sedimentary sequence, we'll have some lateral changes, and every geologist recognizes that there are some lateral changes. And the question is whether these lateral changes are due to change in age, or it is just because of the facet change in the sequence. So that's one important question here. And the other one is it possible to have a uniform stratigraphy from east to west? And I will show some examples of this uniform stratigraphy in the next slide. Next please. This is a map by Fuchs and Frank, and they have divided this area of West Nepal into inner belt and outer belt, and they did find some facet changes, and the dolomites over here, carbonates here, they call coal, limestone, and in the inner belt they call shali. And they are of the opinion that they are of the same age, just some facet changes. And they use these names from India, from Simla area like Simla Slate, Chandpur, Philite, Nagpur, Daini, Rohtal, and others. So, and in their paper of 1970, they have made very extensive discussion of the geology in that paper, and just I want to show you some of the writings. You see, in each paragraph, almost every page contains some information containing, describing that there are some changes. You can read this. That you can see that everywhere they are writing that there are significant lithostratigraphic changes and facet changes, missing rocks and reappearing new rocks like relief slates. But nonetheless, they follow the stratigraphy of road belt. They are all the similar area. So the question is, how far can we extend the names when there are so many changes in lithofacies and composition of rocks? Next one. This was one of the best maps, I think, of West Nepal, prepared by Olsen and others. And in every detail, they have mapped out the units here. We can see a large anticline in the center. And then we have all these blues, which are basically slates, graphic slates, dolomites, carbonates, and quartzites here. And this map, was prepared independently of the another map prepared by Stockley just east and south of this. This is the inner belt. And if we compare these two maps, they are surprisingly similar, stratigraphic units. Though, and I can show you from another map. This stratigraphic unit from here to here is very much similar to that of Stockley. Next, please. Stockley worked out in central Nepal, as you can see, and he mapped a large area. It's just a part of it. He has mapped almost double of this map, and he developed this stratigraphy even here. So, next, please. Yeah, this is his first publication in 1977. We see a large number of stratigraphic units as well as some members, here, and the details are given in his report. And the report contains pages, many pages of description of each unit as well as a location-wise, sheet-wise description. And that is an excellent example of stratigraphic work in central Nepal. Next, please. Here, for example, we see his column, generalized column, and all these names, Fakuk, Nunpu, Darin, these names come from this part of Trishuli River and Maliku, and in this small part, they have worked out stratigraphy and gave this name from the type locality. So this is very important that they have observed these things and measured, and they compared, with other parts. Next one. So here, for example, Fakuk quartzite. Actually, Fakuk quartzite is not a single band. It has 3 bands, and sometimes there could be tectonic, but there are several bands separated by phyllites. So whenever they saw some differences, they noticed that difference and included in the stratigraphy. And similar descriptions are given to each of these rock units in that publication. Next, please. Here I am taking this geological map just to show you some problems we are facing with. Here we have a large number of stratigraphic units. You can see here so many numbers. And let's take a look at these numbers in the next slide, please. You see, this is the stratigraphic given. If you read this one here and this one and this one, you will find the same thing. There is almost no difference between this, and this. Okay? And here we have some red beds, you see, but we will see the red beds afterwards in another unit as well. And these two bands are exactly the same. So they didn't produce any stratigraphic column or any transitional relationships or any contact relationships or internal structures, sectional features, but they just mention different rock names, and they produce these kind of these divisions. And these divisions are very convenient, For example, if you want to make a thrust fault, so you put the lower unit as Sangram formation and the upper unit as the Galang formation. So there will be a thrust fault. If you want to make a fold, for example, so you can put Sangram formation in between the Galang in both sides, and you can make an isoclinal fold. So these kind of things are very convenient to prove your model. Here, for example, bicarbonates are actually the same as these Lakharpada carbonates, they are the same. But here they are put in different units. So this kind of controversy, this kind of confusion is, everywhere. Next one, please. Here you see this formation. Let's take a look at this formation. There is not a single metamorphic rock and igneous rock not mentioned here. So every rock is there. So anyone can be Siri formation. Anyone you like. See? So these are the problems. And funny thing is this one. Very nice is basically intrusion. It occurs in different levels, but it has been named as formation, which is incorrect. Next one, please. Here we have Lakharpada group. Again, we have another formation containing dolomite called Goa formation here, and we saw dolomite in another, and as well as we have this Ramkot formation containing pink, grey sandstone and purple shell and many other things, and again black slates here. So we have these names alone without any interrelationship between these two units, these 3, 4, 5 units, and their internal arrangement. Next one, please. Just take a look at this map, Google map, 70 kilometers you can see. The names come from so many different parts of the country. Like Ganpokhara is from here, Kusma is here, Sangram is here, Ranmatta is here, So there is actually no connection, no stratigraphic, description and relationships, and we are just using these lithological names and we call them stratigraphic. Next one, please. So some attributes of stratigraphy should be followed, for example, using this book, this publication, There is no stratitype, no parastratitype, no contact like transitional contact, rapid transition, sharp, uncontinuity, appearance, disappearance, some bits, textural changes, environmental changes. On what basis we distinguish the formations? Internal arrangement, composition, color, texture, sedimentary, structure, interbedding, intercalation, bed thickness changes, plant alien remains, stomach-like, trace fossils, whatever. And lithologs, nothing is produced. Next one. For example, here you see, this is the gneiss, Uleri gneiss, and it is out of one formation. And this yellow line, you can see one quartzite, and here another. You see, they have been separated by this fault, which doesn't displace anything here, but here exactly, they have two rocks, one older and one younger. And furthermore, this is the younger unit here, supposed to be, but here is supposed to be the older one. So it is very complex, to see the use of these stratigraphic names in these kind of rock units. Next one, please. This is the worst case. Here we see this Ramkot formation, Sangram formation, and many others, and suddenly cut out by a vertical fault. The fault cuts not only these rocks, but all the thrusts also. There is one thrust here, and thrust here, and suddenly we have Bengal slates in between. So it's clear that actually these Bengal slates are nothing but the Sangram slates. You see. These kind of situations are complex. Next one, please. And take another example. Here, the researchers have used this Nurpur formation to separate different units here. This one, and this one, these three units, and this Dali dolomite. Let's take this Nurpur formation from the type locality where Stockholm worked out. And next slide, please. Here, this is the definition of Nurpur formation given by Stockholm. The lower part contains quartzites, as you can see. In the middle part, we have phyllites, basically. The upper part contains dolomite. Basically, some dolomite with slates and other things, So these three things, quartzites, phyllites, and dolomites. But next one.
So the now you have 5 minutes more.
Okay. But here you see that they have phyllites here, no quartzite, they have dolomite in the between, and then again phyllites. So this is nothing to do with this Nurpur formation. Next please. So they also didn't use this map of Sakai, which is very close to it, and didn't extend these units here, including this fault, which should be somewhere here. Next one, please. So here I just want to show you that there are so many stromatolitic varieties in Nepal, and they are all different. Please, next, please. Next one, please. Yeah, there are different types, as you can see. And here they are overturned, completely upside down. They are right here, and they are also overturned. So they are all different types. Next one, please. And in the columns, you see in India, in Kuma, we have stromatolites here. In Nepal, we have stromatolites in Darjeeling and in Barekul. And next one. Here in Sangha, we have here some stromatolites, and they are very different. The stratigraphy is very different. And next one. Again, we have stromatolites here as well as here. And in Kathmandu area, we have quite different types of stromatolites. And in other parts of the country, we have variety stromatolites in Dam, we have quite different. So in Kerala, we do have stromatolites here and here, don't type. So next one. So we have to try to correlate, we have to try to correlate these rocks, from different parts of the basin. So they are very difficult to correlate simply. And one could be the Darjeeling dolomite, one important band, and this Bengal slates will be another band, and these phyllites and others will be the third important band. So based on this, we can correlate them, but these carbonates are very different. They are like road beds. Next one. In conclusion, we have very different maps, but there is no stratigraphy. Basically, they are the geological map. Some earlier maps, as I showed, are better than the new maps, and then there could be lateral changes, and we can apply the same stratigraphy throughout the country. But some could be important ones like Darjeeling dolomite and Bengal formation. So carbonates are different, and they may belong to very different ages. So it is not possible to use these carbonated stromatolites to correlate all the rocks. Thank you.
Say good afternoon, everyone. Sorry, good morning. It's not afternoon yet. Okay. Thank you, Professor, for your in-depth presentation and critical review on Lesser Himalayan Nepal. It was really interesting presentation. And my query is, you have concluded the presentation, but I want to know your suggestion and way forward. How can we solve this problem? Because being Deputy Director General of Department of Mines and Geology, it is one of my responsibility to prepare maps, and that should be officially used for Nepal and worldwide. So what's your suggestion, what's your way forward on this topic, please?
Thank you. I think we have to follow the standard method of mapping. So that means we first should work out the lithological units by making detailed route maps and making columns, making the lithologs, and then putting some tentative formation names, and then to extend them throughout the area, and then compare them with the other maps, standard maps worked out in other areas. If we can actually extend the existing geological maps from central Nepal towards the west or towards the east, and we can see the changes. If we cannot map continuously, if we are in an isolated area, then we have to name the formations, based on the locality and based on the strata type we have developed. This is the only way. And it's not a good idea just to put the name just based on some mythological event like stromatolite or quartzite or silt. Thank you.
May I just join in? I just want to thank Monica ji for this wonderful suggestion. For that working modality, what to do the working modality? Should there be any working group to take up this task? Are you prepared to make a working group drawing people from different agencies, at least academia and your department of mines and geology, so that we could be very much satisfied at the work of the working group that we discuss together with many other international friends. So there should be a working group. That's my proposition and my suggestion. Thank you.
Thank you. Just I want to answer in 1 minute. Is that all the government, all these private companies and other agencies are using the government geological maps for their hydropower road and other constructions. So it is very important that government makes a group that is responsible for the stratigraphic conditions in the country. Thank you.
Vital sir, I have just to query very shortly. One is overlap with the Monica ji. So if so, because our geological map has the quite variation in stratigraphy. So who should have the responsibility to make the standard one, and how should we start for the standardization of stratigraphy in our map? And what is your suggestion to us and new generations? This is first question. And second, in central Nepal, Stocking has prepared the map, and in western by Sakai, and in Siangja section we have prepared the map. And regarding the carbonate successions, if we see upper part of Norpul, Dhading and Jiku carbonate and Maleku limestone is over there in the central Nepal, and in western section there are Khoraidi, Chapati and so many carbonate units. So exactly how can we correlate them? What is your field experience, please?
We can discuss later because it's a very long question. But I have given the answer in the second last slide, and we can talk later on. Thank you.
Thank you. One more thing, just I wanted to point out here that for Western Nepal geology, team of Professor Desal from Arizona University of Arizona, has done tremendous work, including a lot of field work for almost 10-15 years, and he has published the geological map of that area and a big publication of the Geological Society of America special paper in 2020. I don't know how many of you have that publication. That also will help to some extent to clarify things. They have done a lot of geochronological work and very detailed work along with a lot of structural interpretation. So please, if you don't have those publications, I can help you to disseminate that information. Thank you.
Thank you.
So now we go to the next topic. I hand over this to Mary.
So thank you very much. Our next speaker is Mikhail Kropi. And the topic is the early Jurassic Lithioptis type bivalves built up along the Tethyan margin of Pangaea, Albanian-Nepal connection. So this will be a 15-minute presentation. So Mikhail, if you can go about 12, and then we'll have a minute or two for questions.
Good afternoon, everybody. Namaste. So I would like to invite you to some paleontological, paleobiogeographical, practically, sketch of some distribution of some very special kind of early Jurassic bivalves. Please, could you open my presentation, please? So as you see, this talk will be focused to some very special kind of early Jurassic rocks. Our outdoor teams is international, Polish, Slovenian and Nepalese, as you see. So please, next one. In our case, it's a very special kind of bivalves occur during the early Jurassic rocks. Very huge one. The Renato Pozzenato from Ferrara University in Italy, especially interested in these bivalves as well. As you see, these very giant bivalves unusual when we compare with another Bible. Please, next one. As you see, very long, even half of meter from time to time, very special kind, very thick, very long, but stratigraphically, as you see, occur within some very special event, which occur as one of the 5 events of the gigantic Bibles along the whole Phanerozoic time. Next one. And as you see, the stratigraphical distribution of the Bibles is very limited on time, especially on the Prince-Bachian and early to Archean in age. Please, next one. And as you see along the Alpine, Himalayan orogenic system, we can find several places with these Bibles as well. Next one. Paleogeographically, these Bibles occur around the whole Pangaea, and mainly within the western Tethys, but also on the eastern margin of the Pantalassa Ocean. But in our case, we will focus to the European and Asian one. Please, next one. In Albanian time, we have quite a nice example. Next one, please. So you can see the location of the Albanian along the Alpine structure in Europe. This is the next one. And close to the border between Albania and Montenegro, next one please, you can see, next one, you can see the transborder zone full of the early Jurassic rocks and some other limestones, please. And you can see continuous carbonate sequence which are full of the Bibles, please, next one. And you can see the hash of the distribution of the allochtonic part of these Bibles. From time to time we have some tempestite, very typical for the storm deposits of distribution of the Bibles. Next one, please. But from time to time we can find the very characteristically so-called bouquet as the evidence for the autochtonic position in life position of the Bibles. Next one, please. From time to time, in between our Bibles, our bed full of Bibles, we can find very typically, excuse me, it is not my presentation, sorry. So generally, in between our full of fossils, full of these Bibles beds, we can see, could you give me, please? Thanks a lot. So you can see very typical for the surrounding of the Bible-bearing limestones, cross-bedding Oolitic limestones, okay? Extremely shallow water, like, yes, I will. So, and another extremely shallow water evidences for the sedimentation, you can see in this example, for example, full of the oils, coated grains, typically for the extremely shallow water carbonate production. But in this case, in Albanian section, we also found several horizons with plants, absolutely amazing, with some, as you see, the trunk of wood with some pieces of plants determined of the early Jurassic in age, but also have some level with coal. Just below, you can find in this position root systems. Absolutely amazing, very rare record of the plant root system, but in our case, the sediments which occur within the roots and out of the roots are the same, and most probably the root system were empty during the life, and that's why most probably we have the fossil record of the mangroves, which recently occur in the subtropical regions, okay? Additionally, we have several horizons with tempestites, okay? With some corals, with some oysters, but also such absolutely fascinating sample. You can see the root system on the lower part, the tempestite on the erosional base on the upper, and tempestite just above. And that's why we can reconstruct this event like some fighting between land and open marine, with some, let's say, mangrove killed by the storms. Okay? And that's why in our section we have several events with some short episodes of the whole story about the extremely shallow water environment, and then finally killed this mangrove by the stone deposits. And repetition at least 4 times in our fossil record. And that's why this is location of our Albanian type along the southern margin of Tethys. Paleogeographically, when we jumped to Nepal, paleogeographically along the southern margin of Tethys as well, we can see along the Kaligandaki Valley, close to Johnson village, Johnson Formation so-called, and subtropical carbonate platform with oolitic shoals as well. In the field, close to the Johnson vicinity, we have some recumbent fault with some continuous, most probably transition between Triassic and early Jurassic rocks, and that's why close to this lower part of this fault, we can found the same structure with my students as the scale, and the location quite the same, if not identical, oolitic shoal with a cross-bedding structure, with some oncolytic limestones as well. And finally, we found the first time in this place, never published, the same Litiotis type bivalves, full of fossils, most probably constructed some biostroms along this margin of the Tethys, okay? In another place close to, in between the Johnson and Kathmandu, close to the famous Lupra fold structure, you can see again the transition between Triassic and early Jurassic. And where you have the red arrow, you have quite nice outcrop with the same oolitic cross-bedding structure, and again the biostrom in character, the reef type, let's say, biostrom of this full of this lime of this bivalves, with some with some remains of the paleokarst phenomena, and just above of this reddish, this karst phenomena, fossil karst, we have the same bivalves as well, okay? And that's why we can not only correlate, but also we can imagine what happened during those time, during the construction of these biostroms full of Litiotis bivalves, okay? And finally, in between our 2 red dots, we can imagine when we jump to Oman, to Jabal Akdar mountains, practically the same sequence. 1 month ago, I was in the field and studied very precisely bed by bed of such sections, and we found the autochtonic position of the bivalves strictly almost the same, like bouquet in right position, and finally, most probably the same plants. Again, the root system which occur in surrounding beds of this Litiotis bearing limestones, okay? So, finally, as you see, we have along the southern margin of Tethys several points, both with distribution of our bivalves and with some root systems, most probably quite well record of what happened and when happened, both from the animal and plant point of view, and finally some fighting effect between the land and the surrounding shallow water carbonate sea, okay? Just during my first visit of your beautiful country, together with our guider of the Nepalese Nepal Geological Congress 15 years ago, Bishop, sorry, we were a little bit younger. You was our guider, and it was my first time of the touching of personal of the rocks. And then the late Gerard Fuchs, okay, it was my first chance and the last one, unfortunately, to meet with him, and that's why finally. He died, he passed away 5 years ago, and that's why finally I would like to dedicate this talk for him. Okay, thank you very much.
Thank you very much. We have time for a few questions. Okay, in the back. Yes, question in the back.
did you use to characterize the lithotype Bible builders? And what is the methodological approach did your team to correlate Bible builders?
It was the sinking of the soft mud and the upper part just above of the sediment and water boundary, okay? And it was the life position of the Bibles. And that's why ethologically we can interpret what kind of association is autochtonic, what kind is para-autochtonic or allochtonic. For example, during the storm events, during the a little bit remove of the shells, but not transported practically, okay? If, for example, we found several sections with some unisolated two shells of the Bibles, but not on the vertical, but on the horizontal position. And we interpret, okay, that is effect of some very nearby of the place of the life of these animals on a removed just after the storm episode or something like that, okay? And secondly, by the very short stratigraphical range of the Bibles around the whole Pangea, we know exactly that we have some Prince-Bactrian or early Toarcian event full of these Bibles only, never younger, because the Toarcian anoxic event most probably killed not only these Bibles, but several other animals around the whole world, especially within the shallow water carbonate production.
Thank you. Other questions before we move on? Okay, thank you very much, Mika.
Thank you.
Our next presentation is by Lal Prasad Pavel. He's going to talk to us about the lithostratigraphy and age of the Gondwana sequence in eastern Nepal, lithological, paleontological, and paleoflow constraints. Thank you.
Thank you, Mary. Actually, Drona will make presentation. I will assist him.
I am Drona Adhikari and affiliated to Central Campus of Technology of Dharan. And the title of my presentation is the lithostratigraphy and age of the Gondwana sequence in eastern Nepal, lithological, paleontological, and paleoflow constraints. First, talking about the Gondwana sequence. The Gondwana sequence represents the upper Carboniferous to Cretaceous, glacial and glacial-marine, as well as the continental rift basin sediments, which were deposited in the Gondwana land, supercontinent in the southern hemisphere. It is distributed as the isolated basin in both peninsular as well as the extra-peninsular area. Commonly, the time Gondwana is divided into the lower Gondwana, which represents up to the Permian, and the upper Gondwana, which is up to the Mesozoic. And it is characterized by the occurrence of Glossoteris and Pterophyllum flora. In case of Nepal Himalaya, the Gondwana sequence, the rocks of the sedimentary Gondwana sequence can be observed as the lithological patches within the rocks of the lesser Himalaya, and the major deposition, major sections of the Gondwana sequence has been delineated as the red rocks, which is Dang, Tansen, and Barak. In case of eastern Nepal, the lesser Himalaya consists of the individual lithological patches of the Gondwana sequence. And in this study, we are concerned about the Barak as well as Takure section of the eastern Nepal. And the red boxes show the location of the study area. This is the tectonolithostratigraphic shading of the Gondwana sequence of the eastern Nepal. The Gondwana sequence are unconfirmably overlaid on the lake Precambrian dolomite of the lower Noakur group, and it is bounded in south by main boundary thrust, as well as in the north the Noakur complex, Noakur group rocks overlain by the thrust diaphragm as well as similar thrust, and the whole group is placed within the Triveni Taratum group. Previously, several researchers have conducted excellent researches to establish the stratigraphy of this sequence. Still there are some controversy on the stratigraphic shaping of the Gondwana sequence. Firstly, Bosian in 1980 constructed Barak formation for the Gondwana sequence of rock, which consisted 5 lithological units, and with the unit 5 was the youngest, which consisted the siliceous dolomite. Later on, Dhital on 1992 reorganized the lithologies and constructed boracical group instead of boracical formation, which consisted 3 lithological formations: Saptakoshi formation, Koga Dynamic and Bara volcanics, and Tamrang formation in ascending order. He reinterpreted that the youngest siliceous dolomite of Boreal is actually the basement rock, Precambrian dolomite of Lesser Himalaya. In 2018, Bhandari and the team has conducted the geochronology of detrital zircon of the different formation of the Gondwana sequence and re-established the stratigraphy as the oldest Saptakoshi formation of Dhital, and he was reinterpreted as the youngest early Cretaceous or Upper Gondwana sequence. Furthermore, Boral also carried out the geochronology of detrital zircons, and he reinterpreted that previously thought Tamrang formation of Lower Gondwana is reinterpreted as the post-Gondwana sequence. Also, the position of Bara volcanics, as previous authors positioned it associated with the Koka Dynamic, he positioned the Bara volcanics within the rocks of the Saptakoshi formation. As we can see, there are ambiguities in the stratigraphic scheme as well as in the position of Bara volcanics. The objectives of the present study was to clarify the lithostratigraphy and age of the Gondwana sequence. So we applied conventional methods as geological mapping at 1:25,000 scale, root mapping at larger scale is 1:100 and 1:1000, lithological, sedimentological, petrographic study, bathyological study, pellicle analysis, and we coupled these investigations along with the previously published data on detrital zircon by different authors. This is the geological map of the Gondwana sequence of Parashut area. Previously, the researchers were focused only on the eastern flank of this Gondwana sequence, which lasted up to the Saptakoshi river. We have covered all the mythological. We have covered the geological mapping and reached until the western closure, which is near the Rakshik Khola, which is new geological mapping in this area. And the Rakshik detailed geological route mapping was done in some sections. One of the sections was the Rakshik Khola section. It consists of the continuous sequence of lower Gondwana age, which is Koka Dynamic and Tamrang formation. The rocks, the conglomerate containing the cluster of pink and black dirt within the siliceous matrix is alternately overlying the meta-sandstone and phyllite of the Noah group. It is followed by the dynamite containing the cluster of the boulder size of charts of different color. And limestone, dolomites and quartzites, and some boulders of the limestone also present there. The shale and dynamite repeats in the upper horizon of this formation. This formation is separated from the Tamrang formation through the conglomerate, which consisted of the rework class of the dynamite. Rework class, similar class, which is of similar composition as that of cluster of dynamite, and the matrix were coarse-grained sand. These conglomerates were overlaid by the beds of the sandstone, marl and shale, and some sandstone beds with coal pockets, as well as primary structures as cross-bedding, quadrupole and climbing ripples were also observed, and some cruciferous marl beds, as we can see in that photograph, were also observed in the middle and upper horizons, and about 3 horizons of mollusca shale conglomerate were observed within this sequence. These are the photographs of the mollusca shale, and possibly they are the lower Permian cold water bivalve, which is Geodesma. Similar fossil has been recovered from the adjacent region as Ranjan region of Darjeeling area. The Saptakoshi section consists of slightly tectonically complex horizons horizon, as there are several indicators crossing the section. The Gondwana sequence can be divided into two tectonic slices, in which the southern slice is the thinner one and consists of white quartzite, grey black quartzite, coal beds and sandstone, and white paving quartzite of the Southern Formation, which is overlying the stomatic dolomite through alternativity. It is overlain by the similar stomatic dolomite of the Lukwa dolomite. The northern slice consists of the rocks of the Koka, Timikat and Tamang Formation. In Tamang Formation, we find tophaceous sandstone and volcanic plastic sandstones in different stratigraphical horizons, which confirms that this tophaceous and volcanoplastic sequence lies within the Tamang Formation. Furthermore, the top and tophaceous sandstone exhibits stratigraphic layering in some sections, which suggests these top deposits are of detrital origin, and some cast of telespore in the markets also observed in the upper horizons. The photograph is given above. These are the photomicrographs of volcanoplastic sandstone, which comes, and the easternmost section is the Charpes section, which consists of two formations, the Kalikala Formation and Serakola Formation. The area consists of Kalikala Formation, which consists of black and grey quartzite, black shale and white quartzite. Bossial in 1980 recorded lower Gondwana flora, Schizolura gondwanensis. This suggests that this formation should be of upper Permian. The Serakola Formation is in the upper part, and it consists of siltstone and fine-grained sandstone, which consists of the Pterophyllum Benedictarian Rotidophyllum, which suggests the age of this formation should be late Jurassic cretaceous. It is the new finding. And based on the lithological continuity, lithological comparison of different sections and from the primary structures and also the floral and faunal assemblages, we have prepared a unified lithostratigraphic scheme of the Gondwana sequence of eastern Nepal. The Tamang Formation and Kalikala Formation is correlated with Tamang sandstone. The Serakola Formation is correlated with Taltung, and some of this formation can be correlated with lithologically with the Omide Formation. The conclusion: the Gondwana sequence can be divided into 5 formations: Koka Timikat, Tamang Formation, Bora Volcanics, and Kalikala Formation, belonging to the lower Gondwana, and Serakola Formation and Southwest Formation belonging to the upper Gondwana. Upper Gondwana plant process Pterophyllum has been recorded for the first time in Serakola area in East Nepal. Similarly, Bora Volcanics is the reworked volcanic material probably from older volcano, and Tamang Formation, previously thought as lower Gondwana and post Gondwana, has been confirmed as the lower Gondwana based on the effects of oil and cold water bivalve. Similarly, the Southwest Formation, previously thought as the oldest unit of the Gondwana, should be the late Cretaceous or younger based on the detrital sequence as such by different authors previously. The lithological characteristics of this formation are similar to the Omide Formation in the Tanzan area. Thank you.
Thank you. So we've got time for a few questions. Okay. Well, thank you very much. So we'll move on to our final presentation of this session. And this will be presented by Peter Haproff. And the topic is Cenozoic structural framework and crustal shortening of the Himachal-Tibetan Himalaya, northwestern India, implications regarding conflicting thermobarometry and stratigraphy.
All right, can everyone hear me? Great. All right, thank you very much. As Mary mentioned, my name is Peter Haproff. I'm an associate professor at University of North Carolina, Wilmington in the US. This is my first time to Nepal, so I hope it's the first of many trips. Most of my work has been in northwestern India and northeastern India. So for today's talk, we're going to go to northwestern India, and I'm going to talk about the Cenozoic structure of the Tethyan Himalayan sequence in Himachal Pradesh. And I'm going to talk about implications for testing the viability of something called non-lithostatic pressure, or also called tectonic overpressure, where essentially pressure does not equal rho GH or rho GZ. My apologies. So a little bit of background information here. The Tethyan Himalayan sequence, as many of us know, consists of Paleoproterozoic to Eocene sedimentary rocks, volcanic rocks. And those are unmetamorphosed to green schist to amphibolite facies. And in this simplified geological map of the Himalayan origin, you can see here the Tethyan Himalayan sequence is shown in this green color. So these rocks are in the hanging walls of the South Tibetan Detachment. South Tibetan Detachment, or STD, is shown here in this red line. And it's the Tethyan Himalayan sequence is also in the hanging wall of the Great Counter Thrust, or also called the Renbu Sidong Thrust. And that's shown here with these two triangles marking the hanging wall side. Now, the Tethyan Himalayan sequence is often interpreted to represent the distal portion of the greater Indian passive continental margin, so the furthest north portion of that passive margin, greater India, before it collided with Asia. Okay, now, the Tethyan Himalayan sequence, there's been few crustal shortening estimates across it compared to structurally lower lithotectonic divisions or units like the lesser Himalayan sequence, sub-Himalayan sequence. In fact, the greatest minimum estimates for the Tethyan Himalayan sequence is about 150 to 170 kilometers in Ladakh and Zanskar, northwestern India, in this region here, and that's by Mike Searle and others. Now, this amount of shortening, this starkly contrasts that of structurally lower lithologic units or lithotectonic units, like the lesser Himalayan sequence or the sub-Himalayan sequence. In some places, like in western Nepal, there's thought to be over 500 kilometers of shortening. Now, a lot of the shortening estimates for the Tethyan Himalayan sequence, you can see them here on this map from Searle et al. 97, Rochbacher et al. 1992, 1994. This is the shortening magnitude. This is the shortening strain. Now, these numbers are great, but one thing that's really important to know is these are minimum estimates, right? A lot of them are based on balanced cross sections. There's a lot of internal strain in these rocks. There's internal folding, internal shear. So these are minimum estimates. The actual amount of shortening is probably more. Next slide. Okay, now, this discrepancy between shortening in the Tethyan Himalayan sequence and that of structurally lower lithotectonic units, it really is highlighted or relevant in the Himachal Himalayas. And so that region of the Himalaya is shown here in this yellow box. One estimate is from Weismeyer and Graceman 2002. Only about 13 kilometers of shortening and 29% strain. And that comes from the retrodeformation of this balanced cross-section you can see here. So next slide, we're going to zoom in on this box. Thank you. Okay, so that box here corresponds to this geologic map you can see here. The Tethyan Himalayan sequence is shown with these green rocks here. Here's the South Tibetan Detachment right there. And then you have the Greater Himalayan Crystalline Complex shown right there in the purple, just to get your bearings. Here's the Nadir Ophiolite up here in this Yarlung Suture Zone, and the Great Counter Thrust there. Now I mentioned Weismeyer and Graceman, they estimated a minimum shortening of 13 kilometers or 29% strain, and that was in Pin Valley in this region right here. And you can see these yellow lines correspond to where their cross-sections were drawn. So you can see it's really just this frontal part, or southernmost part of the Tethyan Himalayan sequence here. Now another thing that's interesting about the Tethyan Himalayan sequence in Himachal Pradesh is that there's relatively minor internal deformation, and that's evidenced by relatively undeformed fossils, trilobites, primary sedimentary structures like crossbeds, and structural reconstructions of the Tethyan Himalayan sequence here are, they show that the stratigraphic thickness of the section is about 10 kilometers or so. Okay, so here is a stratigraphic column of the Tethyan Himalayan sequence in Himachal Pradesh. I mentioned that Weismeyer and Graceman, based on their structural reconstructions, about 10 kilometers thick or so. Now, the base of the section is the Haimanta group, and there's something really interesting about the Haimanta group. It contains, next slide. Yes, here we go. So the Haimanta group contains kyanite and starlite schists, and thermobarometry on these rocks, they yield peak pressures of about 7 to 8 kbar, and temperatures maybe in the range of 600 or so degrees. Now, if you assume lithostatic conditions, those pressures right here, they equate to a burial depth of 27 to 30 kilometers. So that's quite deep. That's up to 3 times deeper than the estimate of the stratigraphic burial, 10 kilometers or so from, again, structural reconstructions. So here in the strat column, this big section right there, that's the Hymontic group, and that's right here, the basal part is where these kyanite starlight schists are. And then here is a picture of one of the outcrops there from a field season a couple of years ago. Now, these elevated pressures here, this discrepancy between the stratigraphic burial estimate and the lithostatic estimate, that brings up the question, could the elevated pressures be a product of non-lithostatic conditions or tectonic overpressure? And I mentioned that's where pressure does not, under certain conditions, doesn't equal density times gravity times depth per Z. Next slide, please. Okay, so that leads to the research questions for this particular talk. So first, we were interested in what is the structural framework and crustal shortening of the Himachal-Tethyan Himalayan sequence? What is the structural burial depth? Can we, try and estimate that and see if it's correlative or similar to that of other structural reconstructions? Is there evidence for deep crustal burial to 27 and 30 kilometers depth? And is there evidence for crustal attenuation or crustal thinning where the section was that thick and then was thinned to about 10 kilometers or so? And then lastly, is non-lithostatic pressure viable based on structural observations? Okay, so here are our observations. And this is focused on Spiti Pin Valley, which is one of the traverses we did across the Tethyan Himalayan sequence here in Himachal Pradesh. So this geologic map, I know there's a lot on it, may not be able to see a lot of the detail, but we mapped along it, and the major observations is that the lower to the upper sections of the Himachal-Tethyan Himalayan sequence, they're shortened by at least 9, mostly northeast dipping thrusts that are largely expressed as fault propagation folds we interpret. So I'll show you a cross-section here in a bit of those fault propagation folds. But here's a photograph. This is the basal part of the Tethyan Himalayan sequence. And so here's the interpreted version. You can see this thrust here. This is the Hymontic group, which is thrust on top of the Thapele Lipac sequence, which is Ordovician to Carboniferous, right? Next slide. Okay, so here is the balanced cross-section across Spiti Pin Valley. Now, we interpret that those thrusts, they're branched from a single décollement here that goes down to about 10 kilometers depth or so. Back here in the hinterland, that décollement is formed by the South Tibetan detachment there, so it goes down at low angles. It has a shallow dip to it, and then comes up here as the great counter thrust system. There, and then they young to the orogenic foreland to about 5 MA. I think the older ages, they essentially represent the timing of shortening there, Tethyan shortening, and then as you get younger, it might pick up the greater Himalayan crystalline complex coming through, bringing up these rocks, exhuming them, causing them to cool, and then the very young ages might represent some sort of climatic signal, increased precipitation. We're not sure. Now, one sample that we had was quite old at 141 MA. That comes from the uppermost part of the Tethyan Himalayan sequence. And that, I'll talk about this sample later, but it's important because the uranium, thorium, helium date is actually older than the depositional age of the rock there. So that suggests that the rock is thermally unreset and it has implications for its burial. Now, based on the reconstruction of this cross-section, you can see down here, the stratigraphic thickness we interpret is about 13 kilometers, which is relatively consistent with that 10 kilometer estimate. And then the minimum crustal shortening across the Tethyan Himalayan sequence there is 30 kilometers or 22% strain. Again, this is a minimum. There is internal shortening in these rocks. And I'll show that here in a bit. Okay, so that was Spiti Pin Valley. So now we're going to move to the southeast to Sutlej Valley. And so in this region, the lower to middle Himachal THS, the Tethyan Himalayan sequence, is shortened by at least 4 mostly southwest dipping thrusts. So the Sutlej Valley is located right here. This was Spiti Pin Valley. We're just moving to the southeast. Here's some photographs of these thrusts right there. So thrust there. Those are again dipping towards the southwest. Next slide, please. So here's the geologic map of Sutlej Valley. There's the South Tibetan detachment right there. Then there's these southwest dipping thrusts you can see that we had mapped. Next slide. Okay, so now I mentioned that there's internal strain or internal shortening in these rocks. There's folding all throughout the Tethyan Himalayan sequence, and so just a simple sort of back of the envelope calculation, just some bed length, measurements, and then undoing the folds here, you can see that there's about 37 up to 37% additional shortening of these rocks. And that generally agrees with previous estimates of up to 43% in the Himachal Tethyan Himalayan sequence. Okay, so another really important observation here is that just like other people had seen in the past, we saw that there was undeformed fossils, undeformed primary sedimentary structures throughout the Himachal THS, and those include crossbeds, ripples, spherical clasts. And you can see some examples here. Here's some really nice crossbeds. Here's some fossils there, like spherical shaped ones. And then here's some ripples. Now a lot of these, this picture and this picture, those are float, but these are in the outcrop, these are in situ as well. You can trust me on that. Next slide. Okay, so this gets back to the research questions here for this talk. So starting with the first one, what is the structural framework and crustal shortening of the Himachal THS? So I mentioned that in Spiti Pin Valley, here we have northeast dipping thrusts, but then Sutlej Valley, here we have southwest dipping thrusts. So we have a discrepancy there, right? Now why you have this change in the transport directions of these thrusts, just a few kilometers from each other, a few tens of kilometers, there's several possibilities why. One, there could be some sort of tear structure between the traverses, some sort of accommodation structure that is yet to really be observed. One potential candidate is the Korik-Chango Fault, which here was mapped by Joshi et al. 2010. It goes right here, just to the west of Sutlej Valley there. Now this fault has been mapped as a normal fault, but I think a lot is really unknown about it as far as its structural expression, as far as its history, as far as its kinematics. So much should be gleaned from this particular fault. Another potential explanation for this change in the thrust transport direction is perhaps that in Sutlej Valley, these southwest dipping thrusts reflects a different shortening style and a deeper crustal level. Perhaps the Tethyan Himalayan sequence here exposed, it's the lower to middle part of the section, whereas here in Sutlej Pin Valley, it's the middle to upper part of the section. So if there is this perhaps different shortening style, we didn't capture it in the balanced cross section here, but that's one option. Another option is that there's diachronous shortening or shortening at different styles at different times. And so much more work should be done to really parse that out. More mapping, and then also more time constraints. Okay, so talking about shortening then. So I mentioned the Himachal Tethyan Himalayan sequence was shortened by about a minimum of 30 kilometers or 22% strain. So this confirms the significantly less Tethyan shortening than along strike, both to the west and to the east. And in fact, there's much less shortening than structurally lower units in the Himachal Himalaya, as you go to the south, which is about 507 kilometers combined with Greater Himalaya, Lesser Himalaya, and the Sub-Himalayan sequence. That's from Alex Webb, 2013, his balanced cross-section. Now, this discrepancy between the shortening of the Tethyan Himalayan sequence and then the structurally lower lithotectonic units, there's maybe some explanations for this. It could be partitioning of a convergence via strike-slip faulting. So we have the Western Nepal fault system that goes up to the Karakoram fault, so maybe that's taking a piece of the pie. And/or there could be duplexing of other units at depth, which is accommodating a lot of shortening. And so there's decent geophysical evidence of this. This is a cross-section from Gao et al. 2016. So here's the Tethyan thrust belt, and then beneath it, you have potential duplexing of the Greater Himalayan crystalline complex below, which would, again, take up a lot of shortening. So now let's talk about the structural burial depth. So I mentioned that we interpret that the Himachal THS has a maximum stratigraphic thickness of 13 kilometers. That's similar to previous estimates of 10 kilometers. And it also agrees with previous cross-sections for the Tethyan Himalayan sequence, like that from Murphy and Yin, 2003, which you can kind of see here, right there, the colored portion. And also geophysical observations for the decollement depth of the Tethyan thrust belt above the Greater Himalayan crystalline complex. So you can see there's the south bend detachment going like this, kind of right there. There's the geophysical observation showing it, you know, with these sort of undulations to it. This image right here, this is geophysical imagery with a balanced cross-section basically overlaying on it. But anyway, that decollement there, it goes relatively shallow or so, and then about, you know, 10-ish to 20-ish kilometers, depending on where you are. Okay, so now the question, is there evidence for deep burials, 27 to 30 kilometers, or attenuation or thinning of the section?
1 minute.
Okay, I'll speed up here. So there's really a lack of supporting evidence for deep burial, and there's several reasons for this. One, there's undeformed sedimentary features. So I mentioned ripples, crossbeds, spherical clasts, and that suggests no crustal attenuation. You don't see evidence of thinning of the section. Also, few major thrusts are exposed along Spiti Pin Valley, so that reflects a lack of significant exhumation there. Otherwise, those thrusts would be exposed. Here, the Cretaceous uranium, thorium, helium, zircon dates from the uppermost part of the Tethyan Himalayan sequence section. They're older than the depositional ages, so that suggests they were not thermally reset. You know, if they were buried deep down, so they remained, you know, at relatively low temperatures close to the surface. So that, again, that suggests that they were not buried very deep. Also, a 27 to 30 kilometer thick sequence far exceeds that of known passive continental margins. Like, for example, in Western North America, the passive continental margin is about 12 to 15 kilometers thick, about half of that. And then also, again, previous geophysical observations suggest that there's a shallow, relatively shallow decollement above the Greater Himalayan crystalline complex. Okay, so then my last question here, is non-lithostatic pressure viable based on structural observations? Well, I say based on our observations that non-lithostatic pressure remains a promising explanation for this discrepancy. So this is an ongoing project with me and several other collaborators like Victor Guevara, Amherst College, Andrew Souza, at University of Nevada, Reno. And what we're working on right now to try and investigate this further is, one, we're confirming that the elevated, that there are these elevated pressures from thermobarometry. We're also constraining the paleogeothermal gradient of the Himachal-Tethyan Himalayan sequence using stuff like RSCM analyses. And then also determining the timing of peak metamorphism. So the timing that those kyanite starlight schists were generated. They could be Cenozoic, they could be perhaps early Paleozoic, maybe of Pan-African age, and so that would kind of blow this non-lithostatic pressure idea out of the water. So we just performed some lutetium hafnium garnet dating. We're waiting on the results, very excited, so stay tuned for that. Okay, so that's it for this talk here. This is my last slide. I just want to acknowledge my co-authors for this, those who helped. So Dominic Vlaha, Andrew Souza at University of Nevada. Here's myself and my master's student who did the bulk of this work, Evan Branton, Victor Guevara at Amherst College, Francisco Reyes, Amherst, Alex Webb, Marie Genge, Ari Gombat, and Berenja Singh, all very, very helpful in putting this work together. Thank you very much, and I'm happy to take questions.
Thank you.
In this particular case, I don't know. The long answer is there's been a variety of proposed mechanisms for overpressure, like in Nevada and some other places. One of them is like an autoclave mechanism where you have partial melting and then you have local increases in pressure. Another one is there's different rocks have different rheologies to them, different viscosities, and so they'll experience different pressures. Like they'll have different differential stress then, and so then different pressures that they'll experience. There's another mechanism where it's the switching of the tectonic modes from contraction to extension, so then you're rotating your sigma 1 there. And then there's a few others. there. So I'm not sure which one best explains this. We really want to test the viability of it, and then perhaps we can move forward, or someone else can then, maybe some petrologists or something like that, figure out what that mechanism is. But the main implication of this is that this will really change how we understand how rocks experience pressure in origins. And there is a growing body of evidence for non-lithostatic pressure now from several origins.
Thank you. With that, I think we'll adjourn for lunch, and you can feel free to approach Peter if there are other questions. So thank you very much for a nice session this morning.
Thank you for the nice presentation. Now I would like to request the convener of the Nepal Geological Congress, Professor Dr. Khumnarayan Paudel, to hand over the token of appreciation to chair, co-chair, and the rapporteur. So chair, Professor Dr. Vishalnath Uprati. Thank you. Co-chairperson, Professor Dr. Mary Howard. Thank you. Then rapporteur, Krishna Kumar Srestha.